Okay, so we said that a tree is a graph that is acyclic and connex. So between any two nodes, there is exactly one path. We talk about the degree of a node to say the number of neighbors this node has. So the number of edges it is connected to, or the number of vertices it's connected to, because one edge connects two vertices. Branch lengths are not always present in a graph. When we have a tree with no branch length, we tend to talk about a topology, a bare topology. And if you have branch length, this branch length correlates with the amount of time elapsed, or the time or the number of expected substitutions. Because the unit for branch length is the expected number of character substitutions per site when we are talking about a phylogeny built on qualitative characters, on DNA nucleotides, or on amino acids. The tree is rooted if we know where is the most ancient node, otherwise it's unrooted. And very often we don't have any certainty about where is the most ancient point on a tree, and it's not necessarily on a node, by the way. So when we have no information about where is the origin of time in the tree, then we work with an unrooted tree. And we'll see definitions about these in the next slides. In a binary tree, most often we try to have binary trees, or we deal with binary trees because these binary trees are what is the most common product from the phylogenetic inference methods and software. So in a binary tree, all non-terminal nodes have three neighbors. Okay. The leaves are the terminal nodes. And of course, a leaf is connected only to one edge. Okay, so this one edge leads to one neighbor. So terminal nodes, aka leaves, have one neighbor, but in a binary tree, all non-terminal nodes have three neighbors. Okay, so if you see this in an unrooted tree, in the vision of an unrooted tree, then each node has three neighbors, and if you adopt the viewpoint of a rooted tree, then each node has one ancestor and two descendants in a binary tree. Okay. If the tree is not binary, then you may have multifurcations, and a multifurcation is a node with a degree strictly bigger than 3. Okay. So in a rooted tree, a multifurcation happens whenever a node, an internal node, has one ancestor, but more than two sons. So multifurcations are a common way to represent moments of sudden adaptive radiation. So when many species appear more or less simultaneously, I say moment between inverted commas because of course speciation events are in fact taking place over many generations, so over many centuries. So it's not easy to pinpoint what is the moment of speciation, where is the node exactly in terms of its placement on the time scale. But okay, when we have uncertainty about whether a speciation event happened prior to another one or the other way around, then it's understandable that we'll get a tree with a multifurcation. Trees can be built based on a single trait. For instance, one phenotypic characteristic. If we build a tree based on on I don't know, the length of the average length of the upper limbs. Okay, it's an information on which we can build a tree, but we won't have lots of signal in such a tree. So most commonly we use a combination of characters. For instance, align sites make for enough data, 1000 line sites make for enough data to have a tree that is quite robust. We'll see later how to define measures of robustness for a tree. Here is an example of a rooted binary tree. It's a tree on mammals, and yeah, that's just an example of a rooted binary tree. We see it's rooted because we have here this node that has no ancestor. There is no ancestor node to this one. Time goes obviously from bottom to top, okay, because the species are there at on the top, the extant taxa are on the top. So every internal node except the root has one father and two descendants. So for instance, this node has one father, being this node, and two descendants, one here, that is an internal node, and one here, that is a leaf. In this type of representation, the horizontal lines mean nothing, okay? These horizontal lines have no meaning. It's just an artifact in order for us to be able to draw this tree in the fashion of a cladogram. So in terms of branch length, the branch length from the cat to its direct ancestor goes from this point to this one, okay? From the common ancestor of seal and sea lion to the parent of this node, the branch length goes from this to this point, okay? The horizontal part of the branch as it is drawn here has no meaning, conveys no meaning in terms of evolution, okay? It's just to join this point, basically to say that this point is exactly the same as this point in evolutionary terms. We link them with a horizontal line, okay? So there is only one node here with three neighbors, 1, 2, and the third one here. When we have n taxa in a rooted binary tree, you can count on this example. We have 2n-1 vertices and 2n-2 edges, okay? So the vertices, at least we have the terminal vertices, the terminal nodes that are n, and we have n-1 internal nodes, okay? Here we have 1, 2, 3, 4, 5, 6, 7, 8 taxa, so we must have 7 internal nodes, okay? We have 8 terminal nodes plus 7 internal nodes. The internal nodes, I can see 1 here, 1 here, 1 here, that's 3, 4 here, 5 here, 6, and 7. Okay. And edges are 2n-2 edges. Okay. Each of the vertices have one edge connecting it to its ancestor. Okay, for each node you have one edge connecting to its ancestor, except for the root. So you have as many edges as vertices -1. Okay, so 2n-1 means 2n-2. Okay, because this special vertex, that is the root, has no ancestor, so has no edge connecting it to its ancestor. This is not really an edge in a rooted binary tree. This small dangling piece of string here is not an edge. It's just to mention where is the root. Okay. This second example is an unrooted binary tree. And the other difference with the previous tree is that here we have branch length. Okay, here we didn't have branch length. Here we do have branch length. It's unrooted. We don't specify here where is the evolutionary origin, where is the origin of time. We don't know about that. We have branch length. And these branch lengths are obviously much less than 1 in terms of values. There are fractions of the unit. Why is this so? Remember here I said that the unit of a branch length is the expected number of character substitutions per site. Okay? A branch length of 1 would mean that on average you have 1 character substitution per site, meaning that you in fact have no relatedness between the two taxa that are at the two nodes separated by a branch of length 1. Okay. So here, if we have n taxa, we don't have exactly the same number of vertices and edges. In fact, it's easy to see that you can go from a rooted tree to an unrooted tree. How do you do this? You just remove one node, being the root. Okay, if you remove this root, and if instead of having 2 branches here, 1 and another, you say all this is 1 branch. So you merge 2 branches into 1, and you have removed 1 vertex. So you have removed 1 vertex and 1 edge. So instead of having 2n minus 1 vertices and 2n minus 2 edges, in an unrooted binary tree, we'll have 2n minus 2 vertices and 2n minus 3 edges. That's what we have here. Okay? You can count here with this example 1, 2, 3, 4, 5. Taxa, so 5 terminal nodes, and we add 1, 2, 3 internal nodes, so we have a total of 8 vertices or nodes, and 8 is indeed 2n minus 2 when n is equal to 5. And so when you represent an unrooted binary tree, usually it's not oriented like you don't have this pattern that all the leaves are at the bottom and the root at the top, or all the leaves at the top and the root at the bottom. In an unrooted binary tree, usually you have no clear direction from the origin of time to the leaves, simply because the origin of time is not specified, is not made graphically represented. Another representation for trees is the circular representation. That's quite nice. Beware when you see such a tree. Very often the branch length don't necessarily make sense. Okay, so sometimes you will see a tree like this, but the branch length do not convey an evolutionary information of how long was the evolution from Chlamydia, for instance, to its direct ancestor. Sometimes the branch length are just made to fit the picture and to have a nice round circular representation. Here it's the tree of life. Not all the taxa have been have been represented. Not all of the taxa names have been written here, and taxa names here are phylum, or are obviously not just taxa, not just species, but a category that is much higher in the hierarchy of kingdom, domains, phyla, etc. The three kingdoms are represented here, the three kingdoms of life: eukaryotes, archaea, and bacteria. Okay, and obviously eukaryotes, we are somewhere in there, in this animals thing. Okay, so in most software to produce trees, you can choose what type of representation you want. Okay, drawing a tree is something that is an activity on its own, with software that are specialized in representing trees in a nice way. It's an activity that is totally different from inferring the tree, from calculating the tree. Okay, so you can infer your tree with a certain software. There are some formats that are standardized to store trees in a textual file, but then to represent them, to create a picture from this file, is a totally different problem. Okay, so you can have viewers like Archaeopteryx or tree viewer or 3DIN that are good tools to represent trees, and you are free to choose whatever representation you prefer. The tree inference problem is the core problem of phylogenetics. If we assume common descent, if we assume the classical theory of evolution that has been discovered, or let's say the trend of thought has been initiated by Darwin, if we assume common descent, how to derive the most probably correct tree from the knowledge of the traits in the extant taxa. So extant taxa are those taxa from which we can get information today in order to perform this tree inference problem. So most often extant taxa are from species that exist nowadays. Okay, they can be also virus strains that have been sequenced some years ago, so it's not necessarily just today, but in any case the extant taxa are those from which we can get information pertaining to the values of the traits. So here in this example, if we say that the traits are those 4 sites from a DNA sequence, we must have 4 DNA sequences pertaining to each of the 4 taxa. And if I have this alignment as input taxa, as input data, align nucleotides, what can I infer from this in terms of what is the most probable, most probably correct phylogenetic history or evolutionary history? Okay, is this that we had a common ancestor, most ancient common ancestor there, and then we had a speciation giving rise to the species that is the ancestor of taxon 2 and taxon 4? Or is it that then we first had a speciation into taxon 3, and then later a speciation into taxon 1, and then later a speciation into taxon 2 and taxon 4? Okay, so you have many different trees from which to choose from. Okay, to choose from to choose the correct evolutionary history from. Okay, so a tree represents an evolutionary history, in this case in terms of speciation or duplications, but duplications of genes or speciations. But to make it simple, let's say speciation for now. So let's try and tackle a simpler problem, the problem of the evolutionary distance between two sequences. So imagine we have two sequences and they are aligned. First, think about the fact that if you have aligned sequences, it means that you got these sequences and you figured out that they are homologous in a way. Okay, you guess, you assume that in fact these two nucleotides that are aligned come from the same ancestor. That's the basic assumption that you make. And that's the assumption that should have driven the process of aligning these two sequences. For instance, you got these two sequences belonging to two genes performing the very same action, or belonging to the very same pathway, or creating the very same coding for the very same protein in two species, and you decided that it was sound to align them because they must have same evolutionary origin. Okay, so first thing to pay attention to, it makes absolutely no sense to try and create a phylogeny from sequences that are not related, that are not homologous. If they do not come from the same ancestor sequence, then it's hopeless to try and use them to build a phylogeny. But so, coming back to this example, imagine we have these two sequences, and we want to understand first how evolutionary distant are they from each other. Okay? If we imagine that they come from the most recent common ancestor for these two sequences, so we imagine that at some point in the past, these two sequences were not different, but were the same, and they evolved through mutations into sequence 1 and sequence 2. We want to know the evolutionary time separating these two sequences. So we assume that if we wanted to build a tree on these two sequences, we would have such a tree with a certain time here and a certain time there, from the most recent common ancestor to sequence 2, and from the most recent common ancestor to sequence 1. Since sequence 1 and sequence 2 are two sequences we are busy with, we sequenced nowadays, or from the evolutionary viewpoint, they are at the same time. Okay, even if you sequenced one in 2006 and the other sequence in 2015, from the viewpoint of evolution, the difference between these 2 years is not significant. Okay, so obviously it's time 0 here, and here it's a certain time in the past. So the distance between this point and this point is equal to the distance between this point and this point. Okay, so it's sound to say we have the same t here and there. Now the evolutionary time separating the two sequences is 2 times t, because the evolutionary time is the sum of basically it's the length of the path connecting sequence 1 and sequence 2, and this length is 2 times t. So what's this time? First trial to try and get what this time can be, this duration can be. First trial is to say, okay, we're going to get what is the number of differences between these two sequences. So we look at the nucleotides and we see that we have 1, 2, 3 positions where the two sequences differ. Okay, so the first distance we can imagine is to have it in terms of the ratio of sites where we see a difference divided by the total number of sites, which is the length of the alignment. Here the length of my alignment is 10 nucleotides, and I see 3 sites that are different between in sequence 1 and in sequence 2. So I can say my first edit distance is 0.3, okay? 3 divided by 10. Let's have a break here.